Hello, today we are going to see basics of retrosynthesis part 1. Retro is reverse. That is reverse synthesis. We are going to see the basic terms of retrosynthesis. For example, CH3Br, that is methyl bromide, usually we write it's converted into CH3OH by aqueous OH minus. But we are not writing in this how methanol can be prepared. So to find out and to write the synthesis of methanol, to go reverse is called as retroanalysis or retrosynthesis. Retro is written by this arrow. Now, basic terms in retrosynthesis. We'll take for example, we are synthesizing a compound ethanol. So ethanol is our target to prepare ethanol. So it is called as TM. TM is a target molecule. Then we have to select one bond which can be easily broken. So heterolysis of one of the sigma or pi bond is to be carried out. And for example, over here generally a functional group sigma bond is broken heterolytically. After breaking that bond, what we get is CH3CH2 and OH. If the bond breaks this side, it becomes CH3CH2 minus and OH plus. If the bond breaks in the other side, it becomes CH3CH2 plus, that is carbocation and hydroxyl minus. These are the ions after breaking of the sigma bond. These ions are called as synthons. Every breaking of a sigma bond gives 4 ions or 2 ion pairs, that is synthon pair. Now we have to select the correct one out of these 2 synthon pairs, which is more easily available or stable. OH as OH plus is very rare, so it is cancelled. CH3CH2 minus can be obtained but is less stable. OH minus can be easily obtained. Even CH3CH2 plus, that is carbocation, ethyl carbocation is stable, so it is readily available. So the synthon pair out of these 2, which is good, is this one. Next step of this synthesis is to find out the synthetic reagent or synthetic equivalents. If you see ethyl carbocation can be easily available from ethyl bromide, anything which will polarize the bond towards CH2, which will take away electron density by the other group attached to it. Br is more electronegative than this, so any electronegative group will take away electrons from this, and this will become positive, this one will become negative. For OH minus, there are n numbers of alkalis which are equivalents like NaOH. So first thing, its target molecule, this, then the synthons, this, then the selection of correct synthon, and then finding out simple, readily available synthetic reagents. After that, we have to write down synthesis. And how to write the synthesis of ethanol? By doing all these CH3, CH2Br, that is ethyl bromide, on hydrolysis with NaOH, aqueous medium will give CH3OH, CH3CH2OH and NaBr. As we are converting OH, as we are obtaining OH from Br, these two groups are two different functional groups. It may be also called as functional group interconversion. We can see this another method by retroanalysis for the same molecule. Take this sigma bond inside. A shortcut way of showing the mechanism. Converts it into CHO. This is the starting material, and to get ethanol from acetaldehyde, we can reduce it and we can get ethanol from acetaldehyde. This is again a functional group interconversion, and the first one was say CH3, CH2Br, 2CH3, CH2OH by hydrolysis with OH minus. Second is CH3, CHO reduction with any reducing agent, 2CH3, CH2OH. And third analysis, which we will write here, is again by showing it by a short form, converting by moving these arrows simultaneously. That is reaction of methyl minus with formaldehyde. Methyl minus can be obtained by CH3MgBr, where we have to take methyl bromide, then under inert condition we have to prepare its salt with magnesium, in which polarity of CH3 is minus, charge on CH3 is minus and on Mg is plus. When this reacts in inert atmosphere with formaldehyde, it forms OMgBr and CH3. This on hydrolysis gives ethanol. So this is the third method. How we are getting these three methods? By doing retroanalysis. So third, this is one method we are getting, this is second method we are getting, this is third method we are giving. Now what is the use of retrosynthesis? This is the simplest molecule. For simplest molecule, so many methods we can write. Finally, this process should become industrially viable. So we can analyze the various methods by retrosynthesis is the first use of retrosynthesis. Now you can see here it is only hydrolysis. Here it is reduction. For reduction some special conditions are required, special reagents are required. Here it is use of Grignard reagent. To prepare Grignard reagent we require dry ether, we require nitrogen atmosphere, we require special conditions. It becomes this whole process costly. So after analyzing we get three methods for such a simple molecule. Out of these three, this one is the simplest method and we can select on analyzing this correct simple method. Again to repeat the main terms, as this is the first lecture, the meaning of TM. TM is target molecule. What are synthons? The ions obtained after breaking pi or sigma bond, to which are called as synthon pair. For each bond we get two synthon pair. We have to select the most correct synthon pair. Third is synthetic reagent, which is equivalent to this and readily available, and after that writing synthesis. So this is the first simple example. Now everybody, most of you knows meaning of Retro-Diels-Saldar reaction. There also the word retro is used. Retro is reverse. Cyclohexene on Retro-Diels-Saldar reaction gives ethene and butadiene. If you want to synthesize cyclohexene now, why it is called as a retro? Because it is reverse. Meaning of retro is reverse. That's what I want to say. If you want to synthesize this or you want to write the retrosynthesis of this can be shown by arrow like this, that this can be obtained from butadiene and ethene. Now we can go ahead and we'll see one simple example of ethyl cinnamate. Now this is our target. So what we should call it as target molecule. Now which bond is easy to break amongst all these things? Never touch aromatic ring. This bond is easy to break. That too from this pi bond. So we'll go back side. This is the arrow which is required or which is showing the previous state. Plus, minus, plus, minus. These two are called as synthon pairs. Now, minus or plus, whether this synthon pair is good or this synthon pair is good. Minus is next to carbonyl, plus is next to carbonyl, plus is next to benzene, minus is next to benzene. Amongst these two, minus, due to its carbonyls minus I effect as well as resonance, is more stable than plus. So this synthon pair is a good synthon pair. Now we have to write further that which synthetic equivalents or which groups will satisfy these two valencies, which are very common. Plus is balanced commonly by OH and minus is balanced by H plus. So this becomes CH2, this becomes OH. So this one is a beta hydroxy ester. Now previously I have told you how to show the short form by concerted mechanism, this. So one of the starting compound we are getting is benzaldehyde and the another one is CH2 minus. Minus is generally balanced by the metals or by hydrogen. So equivalent for this is CH3COET. This is by doing only one bond cleavage. This can be called as a cleavage, simple cleavage, synthetic equivalent. We have done one group disconnection. This is another term. In this one we have not done any functional group interconversion. This is breaking of bond A. There may be other methods also, but as we have concentrated on only A, this can be called as route A. So this is route or strategy. Another term involved. So now when this, that is benzaldehyde, will react with ethyl acetate under conditions of anhydrous base, that is on hydrolysis will get this product. This on treatment with H plus will get this product. So this is first lecture in which I have tried to tell you basic terms and why and how retrosynthesis is useful. In the second lecture, we'll go ahead, we'll take few more examples, then we'll see what is the linear synthesis, what is a convergent synthesis, and what are various applications by taking examples of some pharmaceutical